For decades, the Apollo missions were about brief visits. As of 2026, the Artemis program has a different goal. We are going to the moon to stay permanently. Surviving on this surface is a cold, mechanical problem. There is no atmosphere to insulate a base, and the lack of a magnetic field means humans are exposed to lethal levels of cosmic radiation. Then there is the regolith. Lunar dust isn't soft, it's chemically reactive and as sharp as shards of glass. It holds a static charge that makes it stick to every piece of machinery we deploy. The temperatures are equally violent. In the sunlight, the surface hits 127 degrees Celsius. In the shadows, it drops immediately to negative 173. Building a home here isn't a matter of bravery, it's a matter of energy. We need a power grid that can withstand an environment where even the dirt is an enemy. Launching supplies from Earth is prohibitively expensive. This forces a strategy called in situ resource utilization, mining the moon's own materials to build and sustain a base. That strategy is energy intensive. Construction robots must use high-heat lasers to melt lunar dust into moon concrete to shield the habitats. The biological requirements are just as heavy. A permanent greenhouse requires constant power for nutrient pumps and specialized LED lighting to keep plants alive in a vacuum. Communication adds to the load. To stay in touch with Earth from the deep craters of the South Pole, we must power a network of relay satellites known as LunaNet. But every one of these systems faces the same wall. The moon rotates slowly, creating 14 Earth days of sunlight, followed by 14 consecutive days of total darkness. This chart shows the danger of that cycle. When the sun sets, the surface temperature plummets to negative 173 degrees. Without a constant heat source, a habitat will freeze to the core long before the sun rises again. A power failure in the dark is a death sentence. Engineers must now decide whether to rely on the established simplicity of solar power or the constant output of nuclear fission. The most common proposal involves placing massive solar arrays on the peaks of the lunar South Pole, where mountaintops see nearly constant sunlight. It's an attractive choice because solar technology is lightweight, well understood, and the fuel source is effectively infinite as long as the sun is up. But solar power has a total failure point. During the 14-day lunar night, energy production drops to zero. To bridge that gap, the solar arrays would need a massive companion, thousands of kilograms of lithium-ion batteries to store 2 weeks' worth of electricity. This illustrates the payload mass penalty. While a solar panel is light, it is violently outweighed by the massive batteries required to survive the night. Launching this weight leaves no room in the rocket for food, water, or tools. While solar arrays are easy to deploy, the mass required for storage makes a 100% solar base financially and logistically impossible. This is why NASA's Fission Surface Power project focuses on a different solution: small modular reactors. A nuclear reactor provides one thing solar cannot: a compact 24/7 baseline of power that is completely independent of the 14-day light cycle. A single reactor producing 40 to 100 kilowatts is more than enough to keep the lights on and the heaters running through the coldest lunar night. However, nuclear brings its own hazards. Launching radioactive material on top of an explosive rocket is a massive safety risk that requires perfect execution. Once it reaches the moon, the reactor must be shielded. Habitats will have to be buried deep in regolith or placed inside natural lava tubes to protect the crew from radiation. This matrix shows the trade. Solar forces us to choose between weight and survival, while nuclear provides constant power but adds significant construction and safety hurdles. Nuclear fission solves the math of the lunar night, but it demands an underground infrastructure that is difficult and dangerous to build. Life support is only the first requirement. The larger mission is to support heavy industrial mining at the lunar South Pole. We need to mine water ice from shadowed craters and use electrolysis to split it into hydrogen fuel and oxygen oxidizer. This turns the moon into a fueling station for the rest of the solar system. We can also bake oxygen directly out of the regolith, which is 40% oxygen by weight. These industrial processes require massive surges of electrical energy, far more than what is needed just to keep the astronauts breathing. As this chart demonstrates, the baseline power for life support is steady, but mining operations create massive spikes in demand. A solar-only grid would collapse under these loads, while a nuclear-only grid would be too heavy to launch. Relying on a single power source leads to a dead end. You either black out during mining or bankrupt the program trying to launch enough reactors. To move from a small outpost to a deep space gas station, we have to move past the idea that one technology can do it all. The debate between solar and nuclear is a misunderstanding of the moon's physics. The environment doesn't offer a choice, it demands a hybrid solution. For those concerned with sustainability, the green solution on Earth becomes a death trap on the moon. The weight of the batteries required for a solar-only base is a physical impossibility. For the engineering realists, nuclear fission is the only way to ensure the colony doesn't freeze. It is the non-negotiable baseline for survival. This quadrant chart plots the risk. Solar-only sits in the low-risk, low-reliability corner. Nuclear-only offers higher reliability but pushes the implementation risk too high. The only path to the top right quadrant, maximum reliability with manageable risk, is a hybrid architecture. The strategy is clear. We use nuclear reactors to provide the non-stop power for life support, and we use solar arrays during the day to power the heavy industrial mining. A functional moon base will be a collection of subterranean bunkers, buried under meters of protective regolith and powered by a shielded nuclear grid. Building this base is the ultimate test of human grit. It represents our transition from being a consumer of Earth's resources to a producer of lunar ones. Survival 238,000 miles away relies on a cold respect for the math of the moon. To stay there, we must build the most resilient hybrid energy grid in history.